Have you ever wondered how scientists peer into molecular interactions like detectives solving a mystery? Enter the world of Fourier Transform Infrared (FTIR) spectroscopy, a powerful tool that allows researchers to analyze materials at the molecular level. FTIR spectroscopy works by measuring the wavelengths and intensities of infrared light absorbed by a material. Each material interacts differently with infrared light, producing a unique spectral fingerprint. This fingerprint helps scientists identify chemical compositions and structural changes. With FTIR, we unlock a deeper understanding of materials, setting the stage to explore its application in adsorption processes. Imagine starting with a blank canvas, ready to capture new elements. In the world of FTIR spectroscopy, this canvas is our adsorbent material before it interacts with any substances. Initially, the FTIR spectra of these materials reveal a lot about their untouched state. We see peaks and troughs that map out the inherent functional groups, each one a clue to the molecular dance about to unfold. These baseline spectra are like the opening notes in a symphony, showing us the bonding structures and chemical environment of the adsorbent. It's fascinating to observe how these structures are arranged before they engage in the adsorption process. This initial analysis not only deepens our understanding but also prepares us to distinguish the subtle yet significant changes that will occur. This baseline is crucial, as it sets the reference point for any changes that occur during adsorption. After exposure to adsorbates, our once blank canvas now tells a complex story. Delving into the FTIR spectra post-adsorption, we observe notable transformations, each revealing critical interactions at the molecular level. First, let's consider the shifts in peak positions. These shifts are pivotal as they signify changes in the chemical environment of functional groups within the adsorbent. For instance, a shift towards lower wave numbers often indicates increased electron density around a bond, suggesting a stronger interaction between the adsorbent and the adsorbate molecules. Next, changes in peak intensity also provide insightful clues. An increase in intensity can reflect a higher concentration of a particular functional group involved in adsorption, whereas a decrease might suggest a masking or interaction that reduces the group's IR activity. Moreover, the emergence of new peaks is particularly telling. These peaks can appear when new chemical bonds form between the adsorbent and adsorbate, or when the adsorbate induces structural rearrangements in the adsorbent. These spectral changes are not just lines on a graph, they are the molecular signatures of adsorption. So why should we care about these molecular signatures? Fourier Transform Infrared Spectroscopy, or FTIR, isn't just about identifying peaks in a spectrum. It's a gateway to understanding complex adsorption processes at the molecular level. By analyzing the FTIR spectra of adsorbent materials before and after adsorption, scientists can observe how substances interact and bind to the adsorbents. This analysis is crucial for enhancing the efficiency of adsorbents in various applications. Whether it's removing pollutants from water in environmental cleanup efforts, purifying active ingredients in pharmaceuticals, or developing advanced materials for industrial use, understanding these interactions allows for targeted improvements in adsorbent design. Each spectrum holds the key to better, more efficient adsorption processes, paving the way for innovations in material science. From invisible interactions to impactful solutions, FTIR spectroscopy guides us through the molecular maze. Today we've explored how FTIR spectroscopy captures the before and after snapshots of adsorbents, revealing the subtle, yet significant changes that occur at the molecular level. This technique has proven indispensable not only in enhancing our scientific understanding, but also in refining practical applications across various industries. By comparing spectra, we can pinpoint the effectiveness of adsorption processes and improve future technologies. As we continue to unravel the mysteries of molecular interactions, FTIR stands as an essential tool in our scientific arsenal.